Today I'm going to tell you about the Szymczak factor in category in very specific context of category of finite sets of finite relations. This is joint one with Marian. Okay, so I will start with a couple ideas behind our motivation to look for the category. Then I will give you some quick details of the Szymczak category and factor. It turns out that we can find in Szymczak category so-called canonical forms. So I will give you some description of this canonical form, but also it is possible to introduce some invariant and classify graphs in the invariants. The main reference for this talk is the preprint, which is right now available on archive. Okay, 2 days ago we had nice tutorials and talks on Conley index theory. Let me just briefly recall and underline one important thing. Namely, if we start with some isolated invariant set, we can find a lot of index pairs for one isolated invariant set. And here on that figure, we have some examples with exit set, which is fig or thin. Okay, all that index pairs isolate the same invariant set. So our expectation is that index give us the same description of invariant set in all those cases. And Szymczak give the most general description of this key feature just to make all those cases giving the same information. So as you see, Szymczak construction is more or less in the heart of index theory, Conley index theory. Other motivation for us was to, in applications we are always dealing with finite sets. So maybe let's look for this Szymczak category for finite sets, and maps is more, maps is not so big. We are like this multivalued flavor. So let's have a look at relations. And of course, relations is the generalization of maps. So also the case of maps is also included in that consideration. So let me just focus on relation. In our preprint, there is also part about the Szymczak category for a category of finite sets and maps also. Okay, so let's have a quick look for some details. What is the Szymczak category? What is the Szymczak factor? We start with any category. Szymczak do not impose any assumption on the category. Category of endomorphism of E-script has as an object pairs. Object from E category and endomorphism from E category, and morphism are all morphism from E category which commutes with endomorphism whose objects are equipped with. And this is category. We start with that category. Next category, Szymczak category, has exactly the same object as category of endomorphism, pair object together with endomorphism. And the construction on morphism is more complicated here. We start with a cross product of morphism from endomorphism category between two objects with natural numbers, and we introduce a relation between those pairs. Those two pairs are related if there exists some natural k such that that equation holds. And this is equivalence. This is an equivalence, so we can take a quotient, and the quotient of this cross product over that relation is exactly the set of morphism in this Szymczak category. The composition is defined as follows. We just compose morphism on the first coordinate. On the second coordinate, we just add natural numbers. And the identity here is given by identity together with 0. Identity on P. This is well-defined category. Szymczak proved it in 1995. There is also some functor which goes from endomorphism category to some to the Szymczak category. It fixes objects, sends the object to the same object, and it maps morphism to the class of that morphism together with 0. And now this is the formalization of this key feature from the point of view of Conley index, namely factor from endomorphism category to some C category will be called normal factor if it sends any endomorphism from endomorphism category to the isomorphism in C category. And as you can expect, as you can guess, the Szymczak factor will be a normal factor. And indeed, for any such a morphism, we take as an inverse identity together with 1. The simple computation shows that in fact it is inverse for this E0 morphism. So the Szymczak factor is a normal factor. And moreover, this is the most general factor, in sense that for every normal factor from endomorphism category to this some C category, there exists unique and prime factor from Szymczak category to this C category, such that that diagram is commutative, or in other words, every normal factor factorizes through Szymczak factor. Okay, that was the most general description of Szymczak category and Szymczak factor. And right now there are some different point of views to this Szymczak category. We can look for the Szymczak category in terms of shift equivalences. For people who from dynamical systems, it's quite convenient. Franks and Mitchell in 1998 proved that two objects in Szymczak category are isomorphic if and only if they are shift equivalent. And other language here, Szymczak category is the localization of category of endomorphism about set of endomorphism from this endomorphism, but not every endomorphism, but this endomorphism which object is equipped with, exactly this endomorphism. So this is different point of view for the same thing here. So now let's go to this very specific context of Szymczak construction for April category. By April, I denote the category of finite sets as objects and binary relation as morphisms. Okay, composition is defined as usual. The powers of relation are just composition of relations. Generalized domain is intersection of all domains of all powers of relation. Generalized image intersection of images of all powers of relation. And invariant part is the intersection of generalized domain and generalized image. And the first observation is that in Szymczak category, if we take any relation, then object equipped with that relation is isomorphic to the invariant part and the relation restricted to the invariant part. What does it mean in practice? I'm used to put some pictures in way of directed graphs. Vertices mean elements of sets. Arrows means that two points are related or in relation. Taking invariant part of relation means that we are cutting off all vertices which are not in connected component or not between connected components. So on the right hand side, we have this invariant part of this relation on the left. The next observation is that we are in finite context. What does it mean? If we start taking consecutive powers of relation, we can only get the finite number of different relations. And moreover, those relations starts to repeat in some periodic way. And we call the number p here an eventual period. And we are interested in any eventual period because in order to get those two equations, equalities here, it is okay for us just find any of these p. It do not have to be the smallest one or just any. And in Szymczak category, any s power of r is isomorphic to the object equipped with r to s plus p, where p is the eventual period. Now let's have a look for some maybe more graph theoretic notions. I call a relation strongly connected if the associated digraph is strongly connected. The period of a strongly connected relation is the greatest common divisor of lengths of all cycles in that graph. From computational point of view, it's okay just to find simple cycles, and those simple lengths of those simple cycles give us also the periods. And it is quite the complexity is linear with respect to the number of sum of number of vertices plus a number of edges. And here we have an example: a cycle of length 4 together with a cycle of length 2 give us the period of that relation equal to 2. Oops. Okay. Just few notions, few symbols here. The arrow here means that 2 points are there's a walk or path from one to the second point. In R, we say the 2 points are strongly connected, and we denote it by double arrow if there is the path from one to the second to the first one. Set X R is the set of all points such that those points are connected with themselves. We are looking for paths of positive lengths, so at least one. Okay, and the relation double arrow is symmetric and transitive. So in this recurrence set here, it will be an equivalence. Sorry for that. Okay. We can refine that relation to the relation tilde R in that way that 2 points will be related by this tilde relation if each path, each walk from X to Y have the length equal to 0 mod the period of the component of those two points. And again, this is equivalence relation, of course, in the recurrence. Okay. And here is maybe some technical theorem, but I think it is important because it shows how this refined equivalence relation field is related to the eventual period. Namely, classes for this tilde relation are exactly intersection of Rp of x together with the strongly connected component of x. Rp of x, I mean all pairs x, y such that x, y
or y's.
Sorry?
Or elements y such that there is a path from x to y and p.
I mean that
you said pairs, but
yeah, this Rp of x is a y. Yeah, you're right. Sorry. Yes, you're right. All set of all y such that the pair x and y belongs to the R2P relation. Yeah. So in particular case of strongly connected relation, the class is equal just to Rp of x. Since this is equivalence relation, we can take the quotient, and on that quotient we can induce some relation R bar, which works like that. Two classes are related if the representatives of those classes are related by R to P plus 1, where P is this eventual period. The relation is well defined because of this congruence condition here. The remote loses connections, I guess. And a theorem here that for any object, we can find this quotient, and in Szymczak category, those two objects are isomorphic. The proof is, of course, constructive, and we have explicit formulas for mutually inverse isomorphism S and T here, and they look like that. All that theorems led us to the observation that there has to be so-called canonical form of object, and the object is in canonical form if it satisfies three conditions. First condition says that each element of relation belongs to the strongly connected component. Second condition says that relation restricted to the connected component is a bijection. And the third condition says that for any n, natural n, R to n plus p is equal to R to n. I mentioned in some proposition a few slides above that this equality holds, but at some point, at some moment of this p. But right now we demand to work it for any n, for any natural n. And here's the example of four relations. All of them are isomorphic in Szymczak category, but only the third one from the left is in canonical form. The first one violates second condition. Second one violates third condition, and the fourth one violates second and first condition. And for each object, we can find object x bar r bar, which is in canonical form, and moreover, those two objects are isomorphic in Szymczak category. And this x bar and r bar here are exactly the quotient of a recurrent set by tilde relation, and r bar is induced by r, as in the previous theorem. And here is an example. Maybe example is not general, but it shows that if you take relation, this is strongly connected relation. Object in canonical form for this strongly connected relation has very specific form. It is bijection, and moreover, it is a cycle, and it works for any strongly connected relation. If we have object in canonical form, and if we take the quotient, we get again canonical form, but those two canonical forms are conjugate in endomorphism category. So it looks like we can right now just restrict ourselves to considering canonical forms, and that's okay for Szymczak category. Yes, and two objects are isomorphic in Szymczak in canonical forms. Two objects in canonical forms are isomorphic in Szymczak category if and only if they are isomorphic in endomorphism category. Now let's have a quick look for the proposition of invariant for these isomorphic object classes in Szymczak category. Let's restrict ourselves to canonical forms and define map on cross product of a connected component in such a way that it measures the length of path between 2 points. As in the example here, L of x prime to x double prime is equal to 2. We are using that function to introduce some relation between different components, two different components, some equivalence relation. And the equivalence relation works like that. We are comparing L function for two components, mod GCD of periods of those two components. This is an equivalence relation, and for example, x prime, a pair consisting of x prime, y prime is related by this relation with the pair x double prime with y double prime. We need that equivalence just to determine number of connections between two different components. And what is it exactly? This is the number of realized equivalence class of that relation by our relation. On that example, I just, to keep that picture clear, I just use some dashed lines in order to avoid, the mess, because the object should be in canonical form, so there should be a lot of other edges. But just to simplicity, look for that. We know that the pair here, I think the battery is gone. For x prime, y prime, and x double prime with y double prime, those two pairs are related by this relation. So for this number of connections, those two edges will be counted as a one class because those two edges are related. Okay. So now we can define the classifying graph. More or less, it is condensation graph of the graph given by the relation, but we have connections between. So we are just shrinking components, and edges are exactly edges between the components with which have number of connections different from 0. And moreover, we use some extra labels for vertices and edges. Vertices are labeled by periods of corresponding components, and edges are labeled by the number of connections between components. And it turns out that isomorphic objects in Szymczak category have the same classifying graphs up to graph isomorphism preserving labels of vertices and edges. And on that example, starting from the left, the first and third relation are quite similar. Both of them have two components of period 2, but the number of connections are different. This first one has the number of connections equal to 2. The second one has number of connections equal 1. So those two relations are not isomorphic in Szymczak category. And here is some, let's say, statistics. We just tried in Mathematica to find different classes for sets of cardinality less or equal to the number of points. And yeah, we see that there is something. There are different classes, even in very small sets. Okay, and to sum up, okay, we know that Szymczak category for a category of finite sets and relations is not trivial. It is quite interesting. We can introduce some canonical form for any object, for any relation. Moreover, there is chance for some nice invariant for the Szymczak category. Yeah, and this invariant can be computable because all that things are the complexity of the more heavy computational task is to just find this eventual period, which is equal to just composing relation, which is exactly the multiplying of Boolean matrices. So that is the hardest part. Okay, and okay, that's all. Thank you very much.
Questions in the audience? I have a general question. So, like in general, this result means that you kind of claim some sort of classification of discrete dynamical systems. I mean, the invariant is
yeah, okay,
strong one.
Not necessarily. I just wanted to say before, thank you, that okay, I have some invariant with some numbers, but I don't understand the meaning of those numbers. Or maybe the periods, the labels of vertices, this resembles somehow the periodicity of component. Yes, okay. But what does it mean exactly, the number on the edge? I have no idea from dynamical point of view. So yeah, this is the classification, but I'm not sure classification of the word.
I think it's clear that you have a tool to distinguish between Szymczak classes. So maybe let me add a comment. Maybe it was not clear from Mateusz's presentation, but the real motivation behind this is that in many problems where the dynamical systems, combinatorial dynamical systems are generated from data, there is no hope that maps, they induce multivalued maps, but for them to get maps in homology, you need the values to be acyclic. And for computer-assisted proofs, this, if you do a good approximation, this is a reasonable assumption. But when you start from data, it's very likely that the values will have some gaps, so they will be not acyclic. So then the realization came that in fact this Szymczak invariant, which is originally used just for in the category of vector spaces, and there is where understood how to compute the Szymczak classes. In principle, it could be used also without this acyclicity of values. And we started with a simple question, because the Szymczak theory is very elegant, very theoretical, but in principle, it might happen, it works for any category, but it might happen that for a given category, the Szymczak category is just trivial. Everything is equivalent. Everything is just due to one point. So the question was whether once we start with the relations, so the next step will be probably linear relations to go back to homology and homology, because you can get, there is no acyclicity, instead of map-induced homology, you get a relation between homology classes. So, but the question was, is there any hope that we'll get an invariant? Maybe once you allow a relation, maybe everything will become equivalent, because it's a quite different between maps and just general relations. The total relation is also present there, which looks like will collapse everything. So that was the positive answer, that at least it looks like it makes sense to go in this direction, because there are different classes and the number is clearly growing when you take a bigger and bigger sets. So this was behind this, and in that sense, it answers the question. But of course, once you see this, you would like to understand more. What is really the meaning of these numbers, as Matej mentioned?
Okay, thank you. Great. Let's time to the speaker again.